Hey there, Organickers. In this video, I'd like to begin introducing you to a few more functional groups. You've already seen alkanes, which have no functional groups, and the alkenes and alkynes, which have double and triple bonds as functional groups, respectively. In this video, I'd like to introduce you to a few more of the functional groups we're going to be studying during this course. A functional group is an arrangement of atoms within an organic molecule which give the molecule its physical and chemical properties. We like to categorize organic molecules by functional group or functional class. It helps us to keep track of those properties. In this video, I'll be covering alcohols, amines, alkyl halides, and ethers in detail. I'd also like to introduce you to aldehydes, ketones, carboxylic acids, and carboxylic esters. Alcohols can be represented by the general formula ROH. A specific example is CH3OH, or methanol. So if I begin with an alkane, and I remove one of the hydrogens, and I replace that with an OH group, that's called a hydroxyl group, by the way, then that would give me an alcohol. What do I mean by this group R? You're going to see this a lot during this course. So R can just mean anything. Some people say that R stands for the rest of the molecule. R could really be just about anything. We use this when we want to talk about a broad class of molecules and not one specific compound. So R could be simply an alkyl group or an aryl group. But the important thing to keep in mind is that the functional group in question should be attached directly to a carbon. Amines are organic molecules that contain nitrogen. So nitrogen can have one R group, two R groups, or three R groups attached to it. Alkyl halides have some organic group, and that will be attached to a halogen, fluorine, chlorine, bromine, or iodide. Ethers have two R groups attached to an oxygen. Aldehydes, ketones, carboxylic acids, and carboxylic esters, you'll often hear me call those just plain esters, but the more precise term is carboxylic esters. These functional groups have something in common. They can be represented by these general structures here, and they all have what we call a carbonyl group. A carbonyl group is a carbon-oxygen double bond. So these four functional groups are distinguished by the groups that are attached to the carbonyl carbon. We'll talk in more detail about these in a later video. Let's talk first about alcohols. As I mentioned earlier, if I begin with a hydrocarbon, and I remove a hydrogen and replace it with an OH or a hydroxyl group, that will give me an alcohol. We distinguish three types of alcohols, or we place them into three different categories according to their structure. We have primary, secondary, and tertiary alcohols, and these are distinguished by the number of carbons attached to what we term the carbonyl carbon. The carbonyl carbon is the carbon that has the hydroxyl group attached to it. So a primary alcohol will have one other carbon attached to the carbonyl carbon. A secondary alcohol will have two other carbons attached to the carbonyl carbon, whereas a tertiary alcohol will have three carbons attached to the carbonyl carbon. Examples of these alcohols would be ethanol, CH3CH2OH, that is a primary alcohol. Isopropyl alcohol, you can see that this carbon here has two carbons attached directly to it, so that is a secondary alcohol. And tertiary butyl or T-butyl alcohol, my carbonyl carbon, has three other carbons attached to it. Let's talk a little bit about the physical properties of alcohols. You should remember from an earlier video that if we incorporate polar functional groups into a molecule, that's going to increase the intermolecular interactions between those molecules. This will in turn influence the boiling points and the melting points. So if I start with pentane. Pentane is just a hydrocarbon with a boiling point of 36 degrees. And I replace one of the methyl groups with a hydroxyl group. That gives me a primary alcohol called butanol. Butanol has a boiling point of 117 degrees. So because I now have a polar functional group, and more importantly, because that functional group is capable of hydrogen bonding, that increases my boiling point and also my melting point significantly. The more polar functional groups we have in a molecule, the higher the boiling points and melting points will be. So you can see that I've added another hydroxyl group to my butanol. So I would call this molecule a diol, and that's increased my boiling point by 100 degrees, pretty significantly. You should also recall that hydrocarbons are not water soluble because they don't have polar functional groups. But my alcohols are water soluble by virtue of their ability to form hydrogen bonds with the water molecules. However, even if you have a polar functional group in a molecule, when the size of the molecule reaches about 5 carbons for every polar functional group, water solubility will diminish significantly. So if we add 1 carbon to our butanol and make pentanol, you see our boiling point goes up a lot, as we expected. This is due to the increase in van der Waals interactions. But you also can see that this 5-carbon alcohol is not soluble in water. When I reach about 5 carbons, the molecule becomes more hydrophobic than it is hydrophilic. The same considerations that we saw with alkanes still apply when we have polar functional groups. For instance, butanol has a boiling point of 117 degrees, but if I look at its branched constitutional isomer, the boiling point is only 82 degrees. And this, you should recall, is because branching reduces the surface area of the molecule, reducing the van der Waals interactions. Alkyl halides, as I mentioned before, are organic molecules that have halogens attached to them. Like the alcohols, we distinguish 3 different types of alkyl halides: primary, secondary, and tertiary alkyl halides. And these again are categorized according to the number of carbons attached to the carbon that bears the halogen. Examples would be ethyl fluoride, a primary alkyl halide, isopropyl bromide, a secondary alkyl halide, and tert-butyl chloride, a tertiary alkyl halide. If we compare the properties of alkyl halides to alkanes and alcohols, we can see that our butyl chloride has a higher boiling point than the corresponding hydrocarbon, but a lower boiling point than the corresponding alcohol. And this is because we do have a polar functional group, but that alkyl halide is not capable of hydrogen bonding with other alkyl halides. If we go from an alkyl chloride to an alkyl bromide, we do see an increase in boiling point. And this is due to the increase in size of the bromine over the chlorine atom. Like hydrocarbons, our alkyl halides are not water soluble because they are not capable of forming hydrogen bonds with the water molecule. Amines are compounds which contain nitrogen, and like the alcohols and alkyl halides, we distinguish 3 types. We have primary amines, secondary amines, and tertiary amines. But we distinguish these according to the number of alkyl or R groups attached to the nitrogen. Now make a note that this is different from the way that we categorize the alcohols and the alkyl halides. These are 3 examples of amines, which are constitutional isomers. They all have the same molecular formula, but their boiling points are very different. Our primary is higher than our secondary, which in turn is higher than our tertiary amine. If we consider the types of intermolecular interactions that amines can participate in, you should recall that most amines can form hydrogen bonds with each other. However, because we don't have a hydrogen on the nitrogen of our tertiary amine, the tertiary amines are unable to form hydrogen bonds with each other. Because the primary amines have 2 hydrogens attached to the nitrogen, they can form more hydrogen bonds. That's why we see this decreasing trend in boiling point as we replace the hydrogens on the nitrogen with alkyl groups. If we compare some of the properties of amines to alkanes and alcohols, for instance, butylamine has a boiling point that is intermediate between the corresponding alkane and the corresponding alcohol. So our primary amine is capable of dipole-dipole interactions, is also capable of hydrogen bonding. The alcohols form stronger hydrogen bonds than the amines. However, because they form hydrogen bonds, amines are often water-soluble, much like alcohols. Ethers are compounds composed of an oxygen with two R groups attached. An example would be this molecule on the bottom, diethyl ether. Diethyl ether is a constitutional isomer to butanol, the molecule directly above it. But you can see that diethyl ether has a significantly lower boiling point. And the reason for this is that diethyl ether cannot form hydrogen bonds with itself. But because diethyl ether can act as a hydrogen bond acceptor, it's moderately soluble in water, whereas the alcohol is soluble in water in all proportions. On this slide, I'm showing you 4 different compounds with 4 different functional groups. We have an ether, an alcohol, or a diol, a molecule with 2 primary amines, and a molecule with 2 secondary amines. The 2 molecules on the top are constitutional isomers, and the 2 molecules on the bottom are constitutional isomers. Based on what you've learned in this video, you should be able to predict the boiling points in a relative sense, or in other words, you should be able to rank these compounds from highest boiling to lowest boiling. Think about this, and we'll discuss it in class.